Hi there, welcome to online lecture number 19. As usual, let's start with our recap. So the last time we introduced the definition of a nucleophile and an electrophile. A nucleophile can be a negatively charged molecule that acts as an electron donor. It usually has a lone pair of electrons. The electrophile, on the other hand, can be a positively charged molecule, and it acts as an electron acceptor. So with the curly arrow, now we indicate the movement of a pair of electrons from the nucleophile to the electrophile, and that leads to the formation of a covalent bond. So to identify the orbitals that are involved in this in the formation of this covalent bond, we need to identify the HOMO and the LUMO that are closest in energy to each other. So in molecule A here, this is HOMO A, and in molecule B, LUMO B. So those are the closest in energy. The filled orbital reacts with an unfilled orbital, that they both have the closest energy match. So we looked at this example of a nucleophilic attack of a hydride on a methanol. So this is the nucleophile, this is the electrophile, and then we looked at the available orbitals that the two reactant molecules have. We find that the HOMO is for the hydride, the nucleophile. It has a filled orbital, and that's the highest occupied molecular orbital, while the LUMO was the pi antibonding orbital between the carbon and the oxygen here, and that is the lowest unoccupied molecular orbital. And in the reaction, these two then overlap, and the electrons jump from the HOMO into the new molecular orbital that constitutes the covalent bonds that is here between the carbon and the hydrogen now. So let's look at the second example, a nucleophilic attack on a C-C double bond. So in principle, a C-C double bond has the same pi bond as the CO double bond that we looked at before. However, in principle, like nucleophiles, they do not attack C-C double bonds, unlike the CO double bond. So this is more of an anti-example and reaction that usually does not take place. And we're discussing now why this reaction doesn't take place. So the first reason is that there is no partial positive charge on either of the carbons, since they both have the same electronegativity, right? So there's no, unlike in the case of the CO, you have a partial positive charge on the carbon, and so there's no real attraction to this C-C double bond for the nucleophile, since there's no partial positive charge. So the second reason are the energy levels of the orbitals that are involved. So remember, in the hydride attack on the methanol, the LUMO was the pi star of the carbonyl bond, right? So here it's plotted. So now let's search for the LUMO of the carbon double bond. So you see the carbon double bond has a pi, of course, that's occupied, but also a pi star, just like the carbon oxygen double bond. But now, because the two carbons have the same electronegativity, the molecular orbitals that can be formed are symmetric in energy, unlike for the CO double bond. The oxygen is lower in energy because of its higher electronegativity, and that causes the pi star to be lower in energy for the CO bond than the pi star for the CC bond. And therefore the LUMO of the CC is higher in energy, and that is a poorer energy match between the LUMO of the CC and the HOMO of the nucleophile, right? So the higher energy of the CC star is resulting in a poorer energy match with the HOMO. So the third reason is that, say, when the nucleophile attacks the double bond, then a negative charge needs to be located on one of the two carbons. But since the carbons are the same, they don't have a high electronegativity, it's energetically unfavorable to have a negative charge on one of the carbons, unlike with having a negative charge on the oxygen, right? So that is more energetically favorable, but for the CC there's no meaning in having a negative charge on one of the two carbons. So these are the three reasons why nucleophilic attacks do usually not take place on CC double bonds. So let's look at a third example, a so-called nucleophilic substitution. So I will discuss this reaction in more detail in the next lesson, but I introduce it here. So here's the reaction equation. You see the nucleophile is attacking this chlorocarbon, and then in the product the nucleophile substitutes the chlorine by itself, and the chlorine splits off as a chloride anion, and therefore this reaction is called a substitution because the chlorine is substituted by the nucleophile, right? So now for us to understand the reaction, we have to identify again the HOMO and the LUMO. So it's easy to find the HOMO. It's just like it was before between the hydride and the methanol. It's the lone pair of electrons in the nucleophile, right? But the LUMO must be some orbital in this chloromethane. So which options do we have? We have sigma bonds only, right? Unlike the last time where we had the methanol with a pi bond also, the pi star was the LUMO, but this time we don't have a pi star and also no pi, and the only bonds are sigma bonds, and they are all occupied by electrons. But that means the lowest unoccupied molecular orbital must be a sigma star, an anti-bonding sigma orbital. So where is that sigma star? It can be either between the carbon and the hydrogens, or it can be between the carbon and the chlorine, right? And so when the reaction then proceeds, the nucleophile will donate its electrons into this sigma star bond, forming a new bond, and not like the last time into a pi star. This time it's a sigma star. So let's identify which sigma star could it be. So you see here the carbon and the hydrogen, they form the sigma and the sigma antibonding orbital, and because both hydrogen and carbon, the orbitals that form these molecular orbitals, they are very similar in energy. This is a very symmetric energy diagram. Now for the carbon and the chlorine, we have less symmetry. Now the sigmas that forms is lower in energy than the sigma between the carbon and the hydrogen, and as a consequence also the sigma star between the carbon and the chlorine is lower in energy, right? Well, and therefore our answer is there. The LUMO must be between the carbon and the chlorine, right? Since it's lower, it's a lower unoccupied molecular orbital. So the electronegativity of the chlorine causes the sigma star to be lower for the CCl compared to the CH, right? So now the sigma bond between the C and the Cl will break and the atoms will separate, and the nucleophile reacts with this sigma star. So now you saw this electronegativity of the chlorine has made the reaction more favorable between the HOMO of the nucleophile and the LUMO of the CCl, and that's the reason why much of organic chemistry is involving functional groups other than carbon and hydrogen, because these electronegative groups like chlorine, they allow for a better energy match between the HOMO of the nucleophile and the LUMO of the electrophile. That's it for this lesson. Next time we continue with more about nucleophilic substitution reactions. See you then.